So next up, we have Isaiah Garrett, Dragonfly Data Compression.
Hey everyone, my name is Isaiah Garrett, and I'm a flight software developer at the Johns Hopkins University Applied Physics Lab, and I'm working on Dragonfly. This talk is a technical look into some of the unique design and operational trade-offs that we're facing on Dragonfly, and how we're going to use data compression to do more science. So where is Dragonfly headed in the first place? Dragonfly is headed to Saturn's moon Titan, which is Saturn's largest moon. It's also unique for a couple different reasons. Titan is the only moon with a substantial atmosphere. It also has liquid methane on the surface, as well as a water ice crust with liquid water underneath. So it's a pretty unique place. In addition, it has abundant complex carbon-rich chemistry in the atmosphere, and that makes it a premier destination to study prebiotic organic chemistry. You can see Dragonfly's landing site on the right of the slide there, that ellipse. That's our approximate landing ellipse, and then you can see our eventual destination, Selk Crater, to the north of that. The distance of that journey is about 180 kilometers. So what exactly are we sending to Titan? So there's three main parts of the Dragonfly spacecraft. The first is this cruise stage, which you can see on the left. This is a more standard spacecraft. It has thrusters, star trackers, and sun sensors. This stage is responsible for actually getting from Earth to Titan and the deep space navigation involved. In the middle, you can see the entry vehicle, which is the EDL assembly and the lander. EDL, this is responsible for the entry, descent, and landing on Titan. It takes about 2 hours from first contact with the atmosphere to actually landing on the surface. Finally, about 1.2 kilometers above the surface, we run into the third part of the Dragonfly trio, which is the rotorcraft lander itself. At 1.2 kilometers, the rotorcraft lander will detach from the back shell, enter freefall, take flight for the first time, and then autonomously navigate itself to a safe landing spot. For the rest of this talk, I'm going to be talking about a key operational trade-off that we're facing, our file compression application, software design, some of our trade studies and benchmarking involved in this effort, as well as some insights into our testing process, and then finally some conclusions and acknowledgements. For our key trade-off, problem one is that we're significantly power constrained. Dragonfly is powered by a multi-mission radioisotope thermal electric generator, or MMRTG, which provides us less than 100 watts of power on Titan. We will need a lot more than this to actually fly. So our solution is to carry a big battery, charge it, and then use the energy in the battery to actually fly. In order to have enough positive power to charge the battery, we'll need to power down most avionics, including flight software, to hibernate and enter a hibernation state. Another problem that we have is that we're significantly bandwidth constrained. Our communication system is going to operate direct from Titan's surface to Earth. This huge distance between Earth and Titan, and the thick atmosphere on Titan, constrain our average downlink to about 2 kilobits per second. This is roughly equivalent to the bandwidth of a dial-up modem from the 1970s. And we expect our total science downlink to be about 6 gigabits. We're also power constrained here too. Avionics on, especially with the radio, will drain our battery. So we have to carefully manage our power. We also have to carefully manage our downlink windows to allow the planets to align and for Dragonfly to see Earth directly from Titan's surface. Taken together, this means that we have a key operational trade-off between our downlink and our flight range. Onboard data compression can help us optimize the amount of useful science data transmitted per bit of downlink. So this is all well and good, but we're here to talk about nitty-gritty engineering details. How does this trade-off actually affect our flight software? Dragonfly is using NASA's Core Flight Executive, or CFE, on top of the VxWorks real-time operating system. This means that we have apps operating in a strict priority-based scheduling environment. The apps can communicate with each other in a pub-sub pattern on the CFE software bus. FC, file compression, is the app responsible for compression and decompression, but we're just going to be talking about compression in this presentation. It can be commanded to compress an arbitrary file, and then it can also be in automatic compression mode to automatically compress files in certain directories. In automatic compression mode, FC follows a simple priority directory regime to prioritize which file to compress next. P0 is the highest priority and P9 is the lowest. The problem is that compression is a really long-running operation. It can take minutes at a time, but we need the app to respond quickly to commands. And the solution is an APL design pattern, which we call deferred commands. For a little bit of context, our task scheduler is very strict. Higher priority tasks will always execute rather than low priority tasks. So this means that starving low priority tasks is a real danger that we have to address. To address this, we use an idle task as the lowest priority task in the system. If this task executes, then we know that we're not starving any low priority tasks and we're at less than 100% CPU utilization. You can also back out your CPU utilization from how many idle task increments you get using a known calibration value. We want to maintain CPU margin for two reasons. The first is that we can ensure that no low priority tasks are starved. And the second is that we have CPU slack available in the system to handle any atypical activity, such as commands that we're receiving, autonomous fault management, or hardware resets. Back to deferred commands. Deferred commands involve a high priority parent task creating a low priority child task to execute long-running operations in the background. In our case, this is file compression creating a low priority task to handle those minute-long compressions, while the parent task can stay awake and handle the high rate, low latency commanded telemetry between apps. For our deferred commands, we've landed on this set of standardized telemetry. The first is a request counter, which is incremented for each deferred command every time we receive that deferred command. The second is a failed counter, which increments every time a deferred command fails to execute successfully. We also have roll-up counters for our mission control. Succeeded is incremented every time any deferred command succeeds for this app, and we also have matching failed and unknown counters. So kind of closing the loop on this design a little bit, the problem is that we have low continuous power from our MMRTG, and our mitigation is to store power in a battery and power down our avionics to conserve energy. The second problem that leads to is it drains our battery to fly or to transmit. And our mitigation is that we perform onboard automatic data compression to optimize the use of that limited bandwidth. Finally, the third problem that leads to is that data compression is a long-running operation. And our mitigation is that the command response and telemetry generation is performed quickly in a high-priority task, while the minutes-long data compression is performed in that low-priority child task. So a little bit more about our actual compression. Dragonfly and FC are going to use the open source bzip2 implementation. A couple of years ago, we performed a trade study comparing the bzip2, gzip, and xz LZMA variants compression algorithms using science and engineering data from a past mission. You can see the results here on the right. We used 3 different block sizes with 3 different algorithms. On the left, you can see that we used a block size of 4096. In the middle, our block size is 65535. And then on the right, we used full file compression. On the y-axis, you can see the compressed file size as a percent of the original file size, so lower is better. You can see that they performed basically all the same, and we intend to use full file compression on Dragonfly, so we'll be using the right side of this graph. We chose to go with the bzip2 algorithm for 2 main reasons. The first is that all the algorithms performed similarly, and then the second is that bzip2 was just the easiest for us to integrate. For more information on this, Brandon Haber gave a talk at last year's Flight Software Workshop going into this in more detail. From here, talking about how bzip2 actually operates, it uses the typical initialize, step until finished end paradigm that's common in compression algorithms like this one. One modification that we've made is that we want to be able to control how much CPU utilization we're using at any given time. We do that by interleaving compression steps with sleeps for a specified amount of milliseconds. For bzip2, the user is responsible for managing the input and the output buffers that you can see on either end of that diagram. In our case, the input buffer is simply read from an uncompressed source file. Compressed data is written into the output buffer, which is then written into our compressed file. bzip2 has an internal work buffer that it manages itself automatically. You can customize that runtime memory allocation by writing your own bzalloc and bzfree function handles. In our case, we just allocate that memory from a static CFE memory pool. As far as commands to the app, there's 5 main commands. The first is the process file command, which you can command it to compress or decompress an arbitrary file on the file system. Say you had a file that you wanted to compress for long-term storage, this is the command that you would send. The second is the abort operation. So this one is important, and it aborts the current compression or decompression operation in progress. This is important because these are long-running operations, and we want to have very fine control of the system. So say you're compressing low-priority large data, and then new high-priority data shows up that you want to start processing immediately. You would send this abort command to stop the low-priority compression and then begin the high-priority compression. Similarly, we have a purge queue of process file commands. There we go. And this is a deferred command to clear the in-queued process file commands. So say you send 3 or 4 of the first command, and then you realize that you have data you actually want to compress first instead, you would send this purge queue command to get rid of those in-queued commands and send your new high-priority command at the beginning of the queue. We also have the set file completion action command. This one just specifies what FC should do with a source file when it is done compressing it. Our 2 options right now are delete or move to trash. Trash in our case is just our /trash directory. Finally, we have the set automatic file compression enable or disable state command. This simply sets a switch about whether we want this automatic compression to happen in the background or not. For our app architecture, this is a very high-level, rough sketch of what it looks like. On the left, you can see the parent task highlighted in green, and on the right, you can see the child task highlighted in yellow. For the parent task, its first thing that it does is initialize the application and spawn the child task. From there, it goes into the main loop and pens on this FC main pipe, which is connected to the CFE software bus. So this is the pipe that it would get commands from the ground system on. It will receive those messages and process them. If it's a deferred command, it will then forward it on to the child task. It will write the command into one of these queues or into the shared variables there, and then send a wake-up signal to the child task. The child task wakes up and then pens on that child signal wake-up queue, either until it receives the wake-up signal from the parent task or a 30-second timeout. It will handle all of the deferred commands on a wake-up and keep processing until it runs out of work to do. When it runs out of work to do, it will go back to the top of the loop and pend on that queue until it gets a signal to do more work. For benchmarking, we do most of our development on an emulated processor running on our personal dev machines. This is awesome. We call it our software in loop, and it's great for rapid development and testing, but it doesn't work for benchmarking performance because it's emulated. To do that benchmarking, we need to actually run on real hardware. Last summer, we did important benchmarking works on this, and I'm excited to share our results. So for our performance, we have a requirement of 1.5 megabytes per minute throughput or greater. And so this begs the question, what CPU utilization percent is necessary to get to that 1.5? We ran this on real hardware using the same real data from the earlier trade study. On the x-axis of the graph, you can see our CPU utilization goes from about 30% up to about 70%. On the y-axis, you can see the throughput goes from about 2 to about 6. So we're well clear of that 1.5 for our 30% CPU utilization, so we have lots of margin and lots of flexibility here. We're pretty excited about that. You can also see our compression ratio on the right side. These are similar to the numbers that we saw earlier. When your compression ratio is above 4, the dot is green. When it's below 4, it's blue. And so we're getting around that performance that we expected. bzip2 also has configuration parameters that we have to sweep. So one is the block size, which is given from 1 to 9, and it specifies the size of that internal work buffer in 100 kilobyte chunks. So a higher number there gives bzip2 more RAM to work with when it's doing its compression. We swept this, and it didn't have much of an effect on our compression ratio. You can see it went from maybe 2.9 at the bottom to 3.1 at the top. So what we set this to ultimately depends on our RAM margins elsewhere in the system. I want to share a little bit of our testing process that we're pretty excited about. We follow a process of integrating early and often with other subsystems. Shown here is the real workflow diagram for this particular integration milestone. Each box is a task owned by a particular team. If the box is green, it's a task owned by the flight software team, and if it's red, it's owned by the ground software team. You can see the interdependencies between tasks highlighted with the connections between boxes. And so this is the real one that we used for this integration milestone. At the end, when we've completed everything, we'll demo it all in front of the rest of the teams. We demonstrated our first end-to-end flight software compression and downlink, followed by ground software decompression and display in our ground system in February this year. At this point, We're working on adding other required features, handling more errors, and getting our business logic ironed out. We also use test-as-you-fly system tests. So as part of our development workflow, we write system-level tests that are run in our ground system. These tests send real commands and assert the real telemetry to make sure the software is operating correctly. We strongly prefer these to source code level unit tests because these tests very closely emulate real operational characteristics. We're testing as we fly. You can see the developer writes test scripts that then go into the ground system. Those scripts send commands that are forwarded over the simulated radio to either our real hardware on a test bed or emulated hardware in our SIL. The hardware then sends real telemetry down back over the radio into our ground system where we assert it and give the test script a pass-fail result. These tests are run nightly in our SIL and on our hardware test beds. We really like these tests because they verify the behavior of flight software, ground software, and even some of our avionics. From here, we talked about the problems and constraints associated with Dragonfly's power, range, and downlink trade-off. We talked about why we have a file compression application on Dragonfly in the first place. I went over some of our APL design patterns and architecture, shared some of our results from the trade study and benchmarking, and then talked about some of our system-level testing processes. For acknowledgements, I want to thank Brandon Haber, who's the Dragonfly Flight Software lead, and who politely listened to many bad versions of this presentation before the one that you're seeing today. I want to thank Amy Alford, who's a developer on the flight software team, who performed the compression algorithm trade study and the results that I shared there. I want to thank Joshua Stone, who was an intern on the flight software team last year, who did that benchmarking on real hardware. And then I wanted to thank the Dragonfly Flight Software team for their patience and their feedback in code reviews, more than 100 comments on this work and counting. So that's everything from me. Happy to take any questions.
All right. So I apologize if you said this, I didn't catch it. Is the FCCFS app open source?
It's not.
Okay.
Unfortunately, it's part of our main flight software at this point, so it's not open source.
Yeah.
Hi, my name's Isaac. Can you talk a little bit about how you orchestrated the test scripts for your integrated system? Are there any specific in-house tools or external tools that you use for that?
Sure. So our ground system comes with a scripting language built in. If you have a particular set of commands that you want to send to the spacecraft, this is what they would actually use in our MOC, our Mission Operating Center, to send commands to the spacecraft at a given time. We use that same scripting language to write these tests, and we've sort of built up utilities in-house to assert values and check tolerances and things like that. So I can't really get into the specific tools that we're using, but we are using exactly the same tools that they would use to actually drive the spacecraft when it's out there.
All right. So online question for your trade study comparing the compression methods. Is time considered as a factor?
It is. We have a maximum file size, and so we can sort of back out how long it will take using our throughput requirements here. We don't have a specific requirement about our maximum compression time. This requirement comes from needing to keep up with our downlink. If we have high priority data coming through, we really want to make sure that this isn't the bottleneck. Does that kind of answer your question?
I would hope so. I'm asking for others.
I understand.
Yeah.
Thank you.
Yeah. So another online question, hardware you're targeting?
I can't share specifics, but
Yep.
it's a common spacecraft processor.
Okay.
It's nothing out of the ordinary.
Multi-core and heterogeneous?
I don't think I can say, sorry.
All right. So could you describe a little more about the challenges and differences between BZIP2, XZ, GZ when targeting into the CFS?
Yeah. We were really looking at whether one of these took far more resources than any of the others, or whether one of them took far less. They all function relatively similarly, but all have different strengths. And so we were really looking for consistent throughput and good enough file sizes, as well as being easy to integrate since we're a relatively small team. BZIP2 ended up being the best across some of those metrics. This one doesn't demonstrate it very well, but there's another graph that is harder to look at that shows many more different data types where BZIP2 consistently gave us the most consistent results. And that's one of the reasons that we went with it. Brandon goes into a lot more information on that in his talk last year.
Hey, I'm Stephen from SwRI. When you were putting together the data that you used to benchmark the compression algorithms, how did you get confidence that the entropy you had exhibited in your data set was enough to match what you're going to be seeing in the world?
Yep, that's a great question. We chose similar instruments from past missions to the instruments that we have on Dragonfly. And basically took those instruments, talked to the people who built them, compared to the data distributions coming out of them, and then used the real data distributions to generate this data that we used here. And so this is real data from on orbit with the realistic entropy within. One danger when doing this kind of thing is benchmarking your compression algorithm using data from on the pad or something like that. But you won't see the real data distribution that way, and your results care about the data distribution. They care about where the data comes from, basically. So that's a great question. And we chose representative instruments and then tweaked it to fit the new Dragonfly parameters for the new instruments.
Could you describe more about the challenge and the difference between BZIP, XZ, and GZ when integrating them to the CFS?
That's a good question. I don't know a ton about that. I sort of have taken the result of this trade study and worked with it. The differences in integration might be covered in Brandon's talk. I apologize, I don't have specifics for you.
All right. So we're going to take one more online and one more here in the room. I'll go ahead and, so a problem with compressed files is that a bit flip can corrupt the full file. How do you compensate for that?
That is a great point, and that's one reason that that it was a hard decision to come to using a compression algorithm on this, because you're right. If you lose one bit, the file doesn't decompress correctly anymore. That is one reason that we typically don't use compression for missions like this, is if you have missing data. You have missing data and you can interpolate, do something on the ground, and that's okay. We lose that ability when we compress these files. That's why it took such an operational challenge, our very low downlink here, to convince us that this was the right call to use this compression algorithm. And in this case, we'll just have to retransmit the whole file if we get an error. We've built a lot of instrumentation on both sides to detect these errors and respond smartly to them.
So,
well, congratulations for the presentation. How many members do you have in the team of the flight software, more or less?
Our flight software team changes over what part of the mission you're in. Right now, we're at about 20 people, and most people are split between Dragonfly and some other projects. So I'm guessing it would come out to about 10 full-time people.
Awesome. So I know I said those were going to be the last, but we have a little bit of time. We're a little early. So how similar is the flight computer to that of Ingenuity? Is it possible to use hardware accelerated compression to improve the compression ratio per watt and lower CPU utilization?
That's a great point. We certainly could use hardware acceleration for this. We do use hardware acceleration on Dragonfly for our autonomous image processing and our landing site identification and navigation to that. So we do use hardware acceleration and custom FPGA firmware to do that. For data compression, we'll be doing most of our data compression while we're sitting on the ground between flights. We'll turn our flight computer on, do our compression, and as part of our downlink, basically. So because these results turned out to be pretty nice, we are able to do this in the CPU, and we don't need to take the time to hardware accelerate it. If we were having to compress as we were flying, or if we were having to compress very quickly and we didn't have all the downtime we expect to have, then we would need to hardware accelerate it. And that's a great point. I've seen that approach elsewhere too.
All right. Thank you, Isaiah. Appreciate it.
Appreciate it.